Good morning to all. I am Ramesh, working as an assistant professor in Department of Mechanical Engineering, St.JOSEPH'S Inst of Technology. So today we are going to discuss about thermal engineering subject. In that particularly we are going to discuss about air standard cycles. First of all, you should know what is meant by air standard cycles. So if normally if you are going to use or if you are going to working in engine, we are going to mix fuel with the air. So major quantity of fuel here is a air. That's why this particular cycle is called as air standard cycles. So in that we have a number of cycles. First one is Otto cycle, diesel cycle, dual cycle, and then Brayton cycle, and then we have Ericsson cycle. Likewise, we have a number of cycles are there. So now we are going to discuss about air standard cycle in that Otto cycle, that is petrol cycle, or we can call it as a constant volume cycle. That is Otto cycle or constant volume cycle. Before getting to the subject, we should have some assumptions to simplify these cycles. First of all, the air which is used in the cycle is assumed as which obeys the gas law, that is PV is equal to MRT, and then the specific heat at constant volume and constant pressure throughout the process is same, and then there is no intermolecular force between the molecules, and then the compression and the expansions are follows the adiabatic process, that is PV is equal to PV power gamma is equal to constant. So these are some assumptions we are going to make to simplify this particular cycle. First I am going to draw the PV diagram for this Otto cycle. Pressure, volume. So this is atmospheric pressure. One, two, three. This is 4. So this 1 to 2 is nothing but isentropic or adiabatic compression. Then 2 to 3 constant volume heat addition. Three to 4 adiabatic expansion, and 4 to 1 is constant volume heat addition. Heat rejection, sorry. So if you take process 1 to 2, that is adiabatic compression. So here we have a compression ratio, that is R is equal to V1 by V2. You know very well, here if you take this one, V1 should be equal to V4, that is constant volume, and this one is V2 is equal to V3. Now this compression ratio we can write it as V4 by V3. Then one more parameter, another parameter is pressure ratio. RP should be equal to P3 by P4, which is happening during 2 to 3 process. P3 by P4, not P4, sorry, P3 by P2. So here, this is heat addition, that is QS. This is QR. and this two 1 to 2 and 3 to 4, which follows the law, that is PV is equal to PV power gamma is equal to constant, that is adiabatic process. These are some basic definition. So what we are going to discuss in this particular cycle is we are going to derive the thermal efficiency of this Otto cycle. So normally you should know what is meant by thermal efficiency. In general, we can write it as thermal efficiency is equal to output by input, where output is nothing but it is a work done. So where we can get the work done, that is 3 to 4. So here output or work done is equal to mCV into T3 minus T4 and then heat supplied Qs, that's equal to mCV into T3 minus T2, where heat rejected QR, that should be equal to mCV into T4 minus T1. Now we can write this efficiency is equal to Qs minus QR divided by Qs. So now we are going to substitute all those formula into this equation and then we can derive the final thermal efficiency. Now efficiency of Otto cycle equal to Qs minus QR divided by Qs. You know very well what is Qs. Qs should be equal to mCV into T3 minus T2 minus of QR mCV into T4 minus T1 divided by heat supply, that is mCV into T3 minus T2. Now we are going to simplify this one. Now I can write this one as, that is 1 minus, we can neglect the common terms mCV, all those terms, 1 minus T4 minus T1 divided by T3 minus T2. Now look at this term, T4 minus T1 and T3 minus T2. Now I am going to change this one, that is either T4 by T1 or T3 by T2 in terms of any one. So for example, if I keep this as constant, that is T4 minus T1, I am going to change this T3 by T2 in terms, change into T4 in terms of, that is T4 minus T1. Now take 1 to 2, process 1 to 2, that is adiabatic compression. So write the relation between temperature and volume. T2 by T1 should be equal to V1 by V2 power gamma minus 1. That is a relation between temperature and volume for adiabatic process. Now this V1 by V2, already I told you R is equal to V1 by V2. So what I am going to do is, I am going to simplify this one, that is T2 should be equal to T1 into R power gamma minus 1. Similar way, take this one, process, that is process 3 to 4, that is also adiabatic process, adiabatic expansion process, where work done we are going to get it, right? So now I am going to write the relation between the temperature and volume. T3 by T4 should be equal to V4 by V3 power gamma minus 1. Now this V4, already I told you, this V4 become V1 and this V3 become V2 power gamma minus 1. Now this T3, now we are going to get T3 as in terms of T4, that is T4 into r power gamma minus 1. Now I am going to substitute this one, that is T2 and T3 in this efficiency equation, right? So efficiency should be equal to 1 minus T4 minus T1 divided by T3 minus T2. Now I am going to replace this T3 as T4 into r power gamma minus 1 and T2 as T1 r power gamma minus 1. So 1 minus T4 minus T1 divided by T4 into r power gamma minus 1 minus of T1 r power gamma minus 1. Now look at this term. Here this r power gamma minus 1 and r power gamma minus 1 are common, so I am going to take it outside. That is 1 minus T4 minus T1 divided by r power gamma minus 1. If I take r power gamma minus 1, remaining term is T4 minus T1. Now you just look at those two terms, that is T4 minus T1 in numerator and denominator also we have T4 minus T1. So I am going to cancel those two terms. So finally efficiency of Otto cycle is 1 minus 1 divided by r power gamma minus 1. So this should be the efficiency of Otto cycle, where already you know very well, where r is nothing but compression ratio. That is V1 by V2. I hope everyone understood this one. Next we are going to discuss about mean effective pressure. What is meant by mean effective pressure? I will explain. Mean effective pressure is nothing but during expansion stroke, the average pressure exerted by the piston is called as mean effective pressure. So normally we are going to find out mean effective pressure as work done, net work done divided by shift volume. Mean effective pressure PM. PM should be equal to net work done divided by shift volume. So now tell me what is, now I am going to discuss about what is shift volume and what is clearance volume. Look at this PV diagram. Total volume, this as, take it as V1, that is total volume. Now I am going to divide this one into 2. This is shift volume Bs and this one is clearance volume Bc. Now total volume where V1 should be equal to Vc plus Vs. What is Vc and Vs? Vc is nothing but clearance volume, where Vs is nothing but shift volume. I will tell you the definition. Shift volume is nothing but during the piston moving from top dead center to bottom dead center, whatever volume occupied, right, that is called as shift volume. And clearance volume is nothing but at the end of compression stroke, there is a gap between top dead center to piston at the top of the piston. So that volume is nothing but clearance volume, right? Now what is net work done? Normally net work done is nothing but area under the curve, we can call it as a work done. So if you look at this one, this PV diagram, this is work given to the system during compression stroke. This is the work given to the system during compression stroke. Similar way, look at this process, that is 3 to 4. Work done by the engine during expansion stroke. I am shaded this one as black color. So this thing is work done by the system. Now what I am going to do is, if you want to get net work done, I am going to neglect the work done during 1 to 2 from work done 3 to 4. That is, work done in 3 to 4 minus work done 1 to 2. You know very well 1 to 2 and 3 to 4 are adiabatic process. So now I am going to write the formula for work done during process 3 to 4. 3 to 4 is adiabatic expansion, that is P3 V3 minus P4 V4 divided by gamma minus 1 minus of work done during process 1 to 2, that is adiabatic compression. I am going to write that is P2 V2 minus P1 V1 divided by gamma minus 1. Now, if you look at the two terms, we have a gamma minus 1 as common, so I am going to take this gamma minus 1 as common, 1 divided by gamma minus 1. Look at this two term, what I am going to do is, that is P3 V3 minus P4 V4. From this I am going to take P4 V4 as common, that is P4 V4 as common. So P3 divided by P4 into V3 divided by V4 minus of, in this term, that is P2 V2 minus P1 V1. From this I am going to take P1 V1 as common, P2 by P1 into V2 divided by V1 minus 1. Now this V4, I am going to replace this V4 as V1. So I am going to take this V1 as common again. So V1 divided by gamma minus 1 into P4 into P3 divided by P4 into this V3 by V4. I am going to replace this V3 as V2, this V4 as V1 minus of P1 into P2 by P1. Already we have a V2 by V1. Now you know very well this V2 by V1, that is R is equal to V1 by V2. Here we have a V2 by V1, so I am going to write 1 by R, that is V1 divided by gamma minus 1 into P4 P3 by P4 into R minus P1 into P2 by P1. This V2 by V1 is again it is 1 by R minus 1. Now we have two terms, that is P3 by P4 and P2 by P1. So I am going to simplify this one. So if you look at the process, that is 3 to 4. Look at the process 3 to 4, that is adiabatic expansion. So I am going to write P3 V3 power gamma is equal to P4 V4 power gamma, that is equal to constant. So now equate these two terms, that is P3 divided by P4 should be equal to V4 by V3 power gamma. You know very well this V4 as V1, this V3 as V2. So I am going to write this term as V1 by V2 power gamma. This V1 by V2 is nothing but it is R. So R power gamma. Similar way, take the process that is 1 to 2. This is 3 to 4. Take 1 to 2, that is P1 V1 power gamma is equal to P2 V2 power gamma, that is equal to constant. So from this I am going to simplify again. P2 by P1 should be equal to V1 by V2 power gamma. This V1 by V2 is nothing but it is R power gamma. So here I am going to replace this P3 by P4 as R power gamma. Similarly P2 by P1 as again R power gamma. So now work done. W should be equal to V1 divided by gamma minus 1 P4 into this P3 by P4 as R power gamma divided by R minus of P1 into this P2 by P1 as R power gamma divided by R minus 1. Now I am going to take this R to the numerator, that is V1 by R power gamma minus 1 into P4 into R power gamma. This R, if you come to numerator, it will become a R power minus 1. So I am going to write R power gamma minus 1 minus of, so here we have minus 1, right? Yes. So minus 1 minus of P1 into this R, again it will come to numerator, it will become a R power minus 1. So R power gamma minus 1 minus 1. Now look at these two terms. Again this R power gamma minus 1 and R power gamma minus 1 is common. So I am going to take again this term as common. So V1 divided by gamma minus 1 into R power gamma minus 1 into P4 minus P1. Now I am going to take again P1 as common. So V1 divided by gamma minus 1 into R power gamma minus 1. Now already I have taken P1 as common. So now this P4 divided by P1 minus 1. What is this P4 by P1? So already I told you pressure ratio, where pressure ratio Rp is nothing but P3 by P2. So now we can write this P3 by P2 as P4 by P4 because this expansion expansion compression takes place at the same range. That's why I am going to take it as a P4 by P1. So this term I am going to replace as Rp. V1 divided by gamma minus 1 into R power gamma minus 1 into Rp minus 1. So this is the work done. So now we are going to discuss, we are going to derive the final step, that is mean effective pressure. So already I told you, right? Mean effective pressure PM should be equal to work done divided by shaft volume. So work done already we have derived, that is V1 divided by gamma minus 1 into R power gamma minus 1 into Rp minus 1 divided by shaft volume, that is V1 minus V2. Already I explained shaft volume is nothing but this is the volume, that is V1 minus V2 or clearance volume. If you neglect this clearance volume from the total volume, we can get the shaft volume, right? Now from this I am going to take V1 as common. V1 divided by gamma minus 1 into V1. So 1 minus V2 by V1. In numerator we have a R power gamma minus 1 into Rp minus 1. So now this V1 and this one V1 gets cancelled. So now I am going to simplify this equation, that is, okay, I will tell you here, P1 into R power gamma minus 1 into Rp minus 1 divided by gamma minus 1. This V2 by V1 is nothing but 1 by R. So 1 minus 1 by R. Now I am going to cross multiply this one. That is P1 into R power gamma minus 1 into Rp minus 1 divided by gamma minus 1 into R minus 1 divided by R. Now what I am going to do is, I am going to take this Rs to the numerator. So mean effective pressure PM is equal to P1 R into R power gamma minus 1 into Rp minus 1 divided by gamma minus 1 into R minus 1. So this is the final formula for mean effective pressure of Otto cycle. Next, we are going to discuss about diesel cycle. So already we were discussed about Otto cycle, and then we were derived a formula for thermal efficiency and a mean effective pressure. So now we are going to discuss about diesel cycle. Diesel cycle, or we can call it as a constant pressure cycle. Constant pressure cycle. Why we can call it as a constant pressure cycle? If it is, that is, the heat added during this process is happening at constant pressure. That's why we are going to call it as a constant pressure cycle. So let me explain what is how the PV diagram comes. Pressure, volume. So similarly, 1 to 2 is 1 to 2 is adiabatic compression, and 2 to 3 constant pressure heat addition, and 3 to 4 adiabatic expansion, and 4 to 1 constant volume heat addition. This is 4. So this is the PV diagram for diesel cycle. I will explain. 1 to 2. 1 to 2 is nothing but adiabatic compression. 2 to 3 is nothing but constant pressure heat addition. That is, P2 should be equal to P3. 3 to 4 is nothing but adiabatic expansion. And 4 to 1 is nothing but constant volume heat rejection. So this is constant volume heat rejection. V1 should be equal to V4. This is constant pressure heat addition. P2 should be equal to P3. This two process, that is 1 to 2 and 3 to 4, follows the law, that is PV power gamma is equal to constant. That is adiabatic process, or we can call it as a isentropic process. 2 to 3 is nothing but, that is QS, and 4 to 1 is nothing but Q rejected, QR. Similarly, we have a term called compression ratio. Compression ratio R equal to V1 divided by V2. And one more term is also which comes into play in this particular diesel cycle, that is called as cutoff ratio. Cutoff ratio. Cutoff ratio is nothing but rho. What is meant by cutoff ratio? So here, if you look at this diagram, 1 to 2, this is adiabatic compression. So once completed this process, the heat addition starts. So which will end at this particular point. So in this area, that is from point number 2 to point number 3, heat addition takes place. So exactly where it will be cut down, that will be decided by this cutoff ratio, that is rho. So that will be defined as volume after heat addition divided by volume before heat addition. So V3 divided by V2, that is called as cutoff ratio, right? And then again we are going to derive the thermal efficiency and mean effective pressure. So first I am going to start with thermal efficiency of this particular cycle. So thermal efficiency of diesel cycle, that is work done Qs minus Qr divided by Qs. You know very well Qs is nothing but heat supply or heat addition, that is takes place during 2 to 3 process, and Qr is nothing but heat rejection, that is takes place 4 to 1, right? So Qs is nothing but heat addition, already I told you, right? Heat addition Qs, that is M Cp into T3 minus T2 divided, that is heat addition, heat rejected Qr is nothing but mCv into T4 minus T1. Now I am going to substitute this one into this equation. That is efficiency of diesel cycle, mCp into T3 minus T2 minus of mCv into T4 minus T1 divided by mCp into T3 minus T2.